The maximum deflection of a cantilever beam of length L with point load W at free end is WL cube by 3EI. The maximum deflection of a cantilever beam of length L uniformly distributed load of per unit length is WL cube by 8EA. In a cantilever beam of length L subjected to uniformly distributed load W per unit length, the maximum అవసరం లేదు. A cantilever beam ఇది A and B formula is 840 sir. The cantilever beam of length L carries gradually varying load from 0 free end W per unit length of a fixed end. The maximum deflection lies at free end. The value of the maximum deflection for a beam given W power 430 EA and the maximum deflection of fixed beam carrying a central point load lies at center of beam. The maximum deflection of fixed beam length L carrying a central point load W is the WL cube by 192 EA. The maximum deflection of fixed beam of length L carrying a total load W uniform distributed load full length is WL cube by 384 EA. Two fixed beam A and B, maximum deflection of beam B is the 1 by 2. The product Young's modulus, the moment of inertia is known as flexural rigidity. Simply support beam A length LB carries load another beam. Same time a gas central equal to double the deflection of the B will be beam double. Simply support beam length LB carries the point of another length, the depth will be double, the deflection of the B will be for the beam A 1 of. This is the wrong and this is the 8 times. 2 carrying point load reflection. This is the 1 by 1/4. ఇట్లా వస్తేనేమో WL cube by 3EI, ఇట్లా UDL ఉంటేనేమో WL cube by 8EI, ఇట్లా టోటల్ UDL ఇస్తే ఇట్లా ఉంటేనేమో ఈ WL cube 48EA, టోటల్ UDL ఉంటేనేమో 5 WL cube by 384EA. అండ్ ఏ విధంగా చుట్టూ అటు ఇటు ఫిక్స్డ్ బీమ్స్ ఉంటున్నాము. B is the WL cube by 192EA, ఫిక్స్డ్ ఉండి మధ్య UDL ఉంటున్నాము WL cube by 384EA. The product of the tangential force acting on the shaft's distance from the shaft is known as twisting moment. When a shaft is subjected to twisting moment, every cross section of the shaft will be under shear stress. The shear stress at the center of circular shaft under torsion is 0. The shear stress at the outermost fiber circular shaft under torsion is maximum. The torsional rigidity of shaft is given by T by T. When a shaft is subject to torsion, shear stress induced at the shaft varies from 0 at the center to maximum at the circumference. The torsional rigidity of shaft expressed by the torque required to produce a twist 1 radian per unit length of shaft rule. For shaft, the shear stress at a point, the distance from the axis of the shaft directly proportional to the polar moment of inertia, a solid circular shaft diameter d pi d power 4 by 32. The polar moment of inertia, hollow shaft outer diameter, inner diameter d is the pi by 32 d power 4 minus d power. Which of the following is the correct torsion equation? T by J tau by R equals C theta by L. The torque transmitted by a solid shaft of diameter d is pi by 16 pi into d cube. Two solid shaft A and B are made same materials. The shaft 50 mm diameter, shaft 100 mm diameter. The strength B as that of shaft 8 times. In the torsion equation, T by J equal tau by R is equal C theta by L in terms of J by R is called polar modulus. The polar modulus for a solid shaft diameter is pi d cube by 16. The polar modulus for a hollow shaft of the outer diameter, inner diameter d is the pi by 16 d power of 4 minus d power of 4 by d. When torque is transmitted by a hollow shaft outer diameter and the inner diameter d is the pi by 16 t into d power of 4 minus d power of 4 by d. A shaft revolving W radians per second transmit torque t, Newton power developed is dash tau W watts. This is the false and this is the 15 by 16. The strength of the shaft is judged by the torque transmitted by the shaft S. Two shaft A and B made up of same material. The shaft A solid and diameter D. Shaft B hollow with outer diameter D is the inner diameter D by 2. The strength of hollow shaft in the torsion is as that of solid shaft is 15 by 16. Two shaft A and B made up of same material which have inner diameter D by 2. The strength of the shaft B as that of shaft A is the 1/8. When two shafts of same length of one of shaft hollow transmit equal torque and have equal maximum stress, then they should be have equal polar modulus. For a two shafts connected in parallel and subjected to twisting moment, an angle twist of each shaft will be same. Yes. The strain energy stored in the solid circular shaft subjected to shear stress is the tau square by 4c into volume of shaft. The strain energy stored in a hollow circular shaft of outer diameter inner diameter subjected to shear stress is tau square by 4c d square plus d square by d into volume of shaft. When shaft of diameter subject to twisting moment, the bending moment then equivalent bending moment m is given by 1 by 2 m plus m square plus t square root of. When a shaft diameter d subject to twisting moment, the bending moment then the equivalent twisting moment given by root of m square plus t square. When a shaft diameter d subject to twisting moment, the bending moment then the maximum normal stress is given by 16 by pi d power of cube m plus m square plus t square. When a shaft diameter d subjected to twisting moment, the bending moment then maximum shear stress is given by 16 by pi d cube m square plus t square root of. A shaft diameter d subject to twisting moment, the bending moment stress is equal to maximum shear developed, then m is equal to t by 2. In spring balances, the spring is used to measure forces. In watches, the spring is used to observe shocks and vibrations low. The spring is cars used to store strain energy incorrect. The springs in brakes and clutches are used to apply forces. A spring when loaded is permanently distorted and recover its original shape when the load is removed. Agree. In watch, the spring is used to store strain energy. The energy is released to run the watch. A spring used to absorb shocks and vibration is leaf spring. The load required to produce a unit deflection in a spring is called spring stiffness. In leaf spring, the maximum bending stress developed in the plates at 3WL by 2N BT square. In a leaf spring, the length of all leaves are equal fast. A leaf spring is supported at the center of the load at the ends. The leaf spring is deflection at the center is the 3WQR cube by 8EN BT cube. When a closely coiled helical spring is subjected to axial load is said to be the torsion. When a closely coiled helical spring is mean diameter is subjected to an axial load, the deflection of the spring is given by 8W d cube n by CD power of 4. When a closely coiled helical spring is the mean diameter is subjected to axial load, stiffness of the spring is given by CD power of 4 by 8 d cube n. Two closely coiled helical spring A and B, the number of turns made up of the subjected to axial load, the mean diameter of spring A double the mean diameter spring B, the ratio deflection spring B spring will be 1 by 8. In the above question, the ratio of stiffness spring B spring A will be dash 8. A closely coiled helical spring in a mean diameter is spring by diameter, the spring index ratio of the C d by d. Two closely coiled helical spring A and B are equal respect to the number of spring A of that of swing B. The ratio of deflection of swing A torsion B is the 1 by 2. The stiffness of closely coiled helical spring is the proportion of the number of turns is the inversely. Two closely coiled helical spring A and B are equal in respect to diameter, whereas in spring A doubled than spring B, the stiffness of spring will be spring A 1/16. Two closely coiled helical spring A and B are equal respect to the number of turns of spring A double that of spring B, the stiffness of spring A will be the spring 1/2. A closely coiled helical spring is cut into two halves, the stiffness of the resulting spring will be doubled. A composite shaft consisting of two step proportion having swing constant K1 and K2 held between two rigid supports at the end. Its equivalent spring constant is K1 plus K2. If the composite shaft in the above equation is fixed at one end and other end is subjected to torque, then its equivalent spring constant is K1 K2 by K1 plus K2. A closely coiled helical spring of a stiffness K cut into equal parts, the stiffness in parts of the spring will be Nk. The rivets are made from a ductile metal is S. For riveting the size of hole drilled in a plate, shank diameter of rivet is greater than. For 25 mm hole drilled in plate's diameter, rivet shank should be 23 mm. According to Unwin's formula, the relation between diameter rivet hole thickness of plate is given by d is equal 6 root t. The rivets are used for fastenings is the permanent. When one plate overlaps the other and two plates are riveted together, two rows of rivet joints is known as double riveted lap joints. When two main plates are kept alignment butting each other riveted with overplate or both sides of the main plates with rows of rivets in each main plate joint is known as double cover butt joint. This is the double riveted. In a riveted joint, when the rivets in a various rows are opposite to each other, the joint is said to be chain riveted. In a riveted joint, when the number of rivet decreases from the innermost row to outermost row, the joint is said to be dash diamond riveted. The center to center distance between two consecutive rivets in a row is called pitch. The distance between the center of rivet hole to nearest edge of plate is called margin. The distance between the center of rivets and adjacent rows of zigzag riveted joint is called back pitch. This is the rivets are generally specified by shank diameter. The objective of caulking in a riveted joint is to make the joint is leak proof. A riveted joint may fail by any one of these. In order to avoid tearing of plate at an edge, the distance from the center of rivet hole to the nearest edge of the plate should be 1.5 d. A lap joint is always in shear single. A double strap butt joint with equal strap is always in double shear. The pull required to tear off the plate by pitch length is P minus D T into sigma T. The pull required to shear off a rivet in double shear, the pitch length is pi by 2 into D square into tau. The pull required to crush the rivet per pitch length is dt sigma c. The strength of riveted joint is equal to the minimum value of P1, P5 or Pc. The strength of unriveted solid plate per pitch length is Pt sigma d. The efficiency of riveted joint ratio of strength of joint is strength of the solid plate is true. In calculating the strength of riveted joint, tearing, shearing and crushing the actual diameter of hole needed for rivet is used. If the tearing efficiency of riveted joint 50% in the ratio of rivet hole diameter, the pitch of the rivets is 0.50. A welded joint as compared to riveted joint has a strength more. Transverse fillet welds are designed for tensile strength. Parallel fillet welds are designed for bending strength is agree. The tensile strength of a welded joint for a double fillet is root 2 S L sigma T. Shear strength of a welded joint for a double fillet root 2 S L tau. Which of the following statement is correct? Rivets are generally specified shank diameter. A pressure vessel is said to be a thick shell. The ratio of wall thickness, the vessel diameter is greater than 1. The pressure vessel is said to be thin shell when ratio of wall thickness vessel into diameter is 1 by 10 is less than. The thick pressure vessel is always used to generation of steam can withstand pressure is the diameter of pressure vessel 15 times of wall thickness vessel should be thick shell degree. As the thin cylindrical shell of diameter length thickness subjected to an internal pressure hoop stress in the shell is PD by 2T. A thin cylindrical shell of diameter length thickness of subjected to an internal pressure longitudinal stress in the shell is PD by 4T. A thin cylindrical shell subjected to internal pressure P ratio of longitudinal stress to the hoop stress is the 1 by 2. The design of thin cylindrical shell is based on hoop stress. The hoop stress is thin cylindrical shell is circumferential tensile stress. The maximum shear stress is thin cylindrical shell subjected to internal pressure PD by 80. A thin cylindrical shell of diameter length L thickness is subjected to an internal pressure. The circumferential hoop strain is PD by 2T 1 minus 1 by 2M. A thin cylindrical shell of diameter length thickness subjected to an internal pressure. The longitudinal strain is PD by 2T 1 by 2 minus 1 by M. When a thin cylindrical shell is subjected to internal pressure, the volumetric strain is 2E1 plus E2. A thin cylindrical shell of diameter length is subjected to internal pressure. The ratio of longitudinal strain and hoop strain is M minus 2 by 2M minus 1. When a thin cylindrical shell is subjected to an internal pressure, there will be an increase in diameter of the length of the shell. The hoop stress is riveted cylindrical shell diameter thickness of subjected to an and internal pressure P PD by 2Tn. The longitudinal stress in a repeated cylindrical shell diameter thickness is subjected to an internal pressure is the PD by 4 to N alpha. A thin spherical shell of diameter and thickness subjected to an internal pressure, the stress in shell material is PD by 40. The maximum shear stress in thin spherical shell subjected to an internal pressure is 0. Yes. Shell of diameter d and thickness subject to internal pressure, the volumetric strain is 3 PD by 40 1 minus 1 by m. A thin cylindrical shell of diameter and thickness subject to internal pressure, the volumetric strain is PD by 40 5 minus 4 by m. A thin cylindrical shell of diameter and thickness is subject to internal pressure, the ratio of longitudinal strain to volumetric strain is m minus 2 by 5 m minus 4. The thickness of thin cylindrical shell with hemispherical ends, the top spherical ends is the more than. The hoop stress, the thick cylindrical shell is maximum at the inner radius true. Lami's theory is associated with the thick cylindrical shell. In thick cylindrical shell subject to the internal pressure, the tangential stress at the thickness of cylinder is the maximum at the inner surface and minimum at the outer surfaces. A thick cylindrical shell subjected to an internal pressure, radial stress across the thickness of the cylinder is maximum at the inner surface and 0 at the outer surface. A thick cylindrical shell subject to internal pressure, tangential stress is always tensile stress, whereas the radial stress is compressive correct. In a thick cylindrical shell subject to the internal pressure, the maximum radial stress at the inner surface of the shell is minus P compressive. A thick cylindrical shell having or not outer and radial subjected to an internal pressure, the maximum tangential stress at the inner surface of the shell is P of R1 square plus Ri square by R1 square R2 R1 square Ri square. A thick cylindrical shell having R0 Ri outer and inner radial subjected to an internal pressure, the minimum tangential stress at the outer surface of the shell is 2P Ri square by R0 square minus Ri square. The maximum tangential stress in a thick cylindrical shell is always the internal pressure acting on the shell greater than. When a column is subjected to an eccentric load, the stress induced the column will be dash direct and bending stress both. If the magnitude direct stress bending stress is equal, then there will be zero stress. One of the extreme ends of the column is agreed. For no tension condition, a base of short column is circular section in a line of action. The load should be within the circle diameter equal to the main circle 1/4. The limit of eccentricity is based upon no tension condition true. The limit of eccentricity for no tensile condition column for circular section diameter d is d by 8. The load at which column just buckles is known as any one of these. For long column, the value buckling load is crushing load is less than. Compression members always tends to buckle in the direction of this least radius of gyration. The direct stress induced in a long column compared to bending stress is negligible. A column that fails due to the direct stress is called a short column. The assumption made of Euler's column theory is that is all of the above. According to Euler's column theory, the crippling load for column length hinged both ends is pi square A by L square. According to Euler's column theory, crippling load for column length fixed at ends, the crippling load for similar column hinged at both ends is 4 times. According to Euler's column theory, crippling load for column of length with one end fixed and other end is free is the crippling load for similar column hinged both the ends less than. According to Euler's column theory, the crippling load for column length will one end fixed and other end hinged 2 pi square A by L square. According to Euler's column theory, crippling load of column given by P is equal pi square A by CL square in the equation. The value of C column in the both ends hinged is 1. The Euler's formula, the value of C, the column with one end fixed and other end is hinged is 1 by 2 is the true. In the Euler's formula, the value of C column in the both fixed is 4 is the and the Euler's formula, the value of C for the column with one end fixed and other end is free 4. A column of length with both ends fixed may be considered as equivalent column of length will both ends hinged L by 2. A column of length with both ends fixed may be considered as equivalent to column of length with one end is fixed and other end is free. This is the L by 4. The equivalent length of given conditions, length of the equivalent column of the same material, the cross section with hinged ends having the value of crippling load equal to that given column is true. For the buckling load for a given column depends upon all of the above. The value of equivalent length to actual length for the ends hinged in the same yes. The relation between the equivalent length and actual length column of the both ends is fixed L is equal to L by 2. The relation between the equivalent length and actual length column one end is fixed and other end is hinged is L is equal to L by root 2. The value of equivalent length, a vertical column has two moments of inertia. The column will tend to buckle the direction of the minimum moment of inertia. The slenderness ratio is the ratio of length of column and least radius of gyration. The column whose slenderness ratio less than 80 are known as short column. In order to know whether column is long short, we must know the slenderness ratio true. A column with maximum equivalent length has one end is fixed, other end is free. Euler's formula holds good only for long column. A column is said to be short column when the ratio of length least radius of gyration less than 80. If the slenderness ratio for column is 100, then the Serrative is column long column. A Rankins formula, a column is sigma C A by 1 plus A L by K whole square. Thus, Rankins constant for a mild steel column both ends is hinged 1 by 7500. The Rankins formula holds good for both short and long column. In case of eccentrically loaded strut is preferred to composite section. A masonry dam may fail due to any one of the above. The order of avoid sliding masonry dam, the force between dam and soil should be least the total water pressure per meter is 1.5 times. In order to prevent crushing a masonry base of dam, the minimum stress should be the permissible stress to the soil less than. The Rankins theory for active earth pressure is based on the assumption that all of the above. When the retained material is subjected to some superimposed subcharged load, the total horizontal pressure due to subcharged load is P into 1 minus sin pi by 1 plus sin pi. The horizontal thrust offered by the retaining wall of retained material is WH square by 2 1 minus sin pi by 1 plus sin pi. The reinforced cement concrete beam is considered to be made up of heterogeneous material. The steel bar in a reinforced cement concrete beam are embedded near the bottom. The assumption made up of theory of the reinforced cement concrete beam is that of all of the above. Thus, critical neutral axis of reinforced cement concrete beam is based on the principle that neutral axis is situated at the center of gravity of the given section. True. The actual neutral axis is reinforced cement concrete beam based on the principle of moment area of compression tension zones of neutral axis are equal to. Agree. In case of under reinforced beam, the depth of actual neutral axis is dash that of the critical neutral axis less than. The moment of resistance to reinforced section is the Bn sigma c by 2 d minus n by 3. In case of over reinforced beam, the depth of actual neutral axis of the same that of the critical neutral axis is the solution. The moment of resistance of balanced reinforced concrete beam based on the stresses is steel and concrete both. In a stress strain diagram for mild steel, A represents elastic limit and the point C represents the lower yield point and point B represents the upper yield point is the right and the point E represents the maximum stress in falls. The stress corresponding point D is the ultimate stress. Ultimate stress is there and stress is proportional to strain. The portion is the from 0 to A. Hooke's law holds good the portion from 0 to A. Agree. The plastic range occurs beyond point A. A tensile test when the material stressed beyond elastic limit is the tensile strain compressed to the stress is increases more quickly. The stress at which extension of the material takes place the more quickly as compared to increase the load called as yield point. The breaking stress is the ultimate stress is less than. The stress developed in the material without the permanent set is called as elastic limit. When the material is loaded elastic limit, the material will be a shape size when the load is removed. Agree. The ratio of the largest load is the test of original cross sectional area. Test piece is called as ultimate stress. The tensile test is carried on material is ductile. The compression test is carried on the material is brittle. The tensile strength of ductile material is compressive strength is greater than. The compressive strength of brittle material is their tensile strength greater than. A tensile test is performed in a mild steel round bar diameter of fracturability decreases. A tensile test is performed in a round bar if a fracture. It has been found that the remains approximately same at a fracture. The material under test was cast iron. The percentage reduction area center specimen made of material under tensile 60%. Percentage reduction of area specimen with the same distance made up of material B, percentage the material A, more ductile material B. A percentage elongation of certain specimen material A and tensile and elongation specimen with same direction is another 40% in the material. For more ductile material A is the right. In stress strain diagram is the curve A represents soft brass, represent glass is the curve C, and curve C represents soft brass, false information. D represents mild steel, yes, okay. And for ductile of material with increases the percentage reduction area of area of a specimen under tensile test is increases. The ductile of the material with the decreases percentage elongation of a specimen under tensile test is decreases. Factor of safety is defined as the ratio of ultimate stress to working stress. The factor of safety always more than unit is the correct. The compression test the fracture cast iron specimen would occur along is the an umbilical plane. A fatigue test is carried out for all of this above. Thank you. SOM completed.